today's lab we're going to look at visible spectroscopy of a potassium permanganate solution. And when we look at the term spectroscopy, spectroscopy is really a study of looking how substances, primarily in this class organic substances, will interact with electromagnetic radiation. Electromagnetic radiation covers the whole gamut of radiation, if you will, starting at the very low energy end where you've got radio waves, and then up to the higher energy end where you've got X-rays, gamma rays, so on and so forth. So if you go from the low end, the radio waves, those substances or that particular type of electromagnetic radiation has the largest wavelength but the lowest frequency and the lowest energy. As you move up from radio waves to microwaves to infrared radiation, infrared radiation is where we're looking at molecular vibrations. Then you move to visible light, Roy G. Biv, if you will. We're looking at the colors of the rainbow. And then as we move up to UV light, ultraviolet radiation, and actually ultraviolet and also visible light both still involve the electronic transitions. And when we say electronic transitions, we're looking at electrons that are going from one orbital to another. And in organic chemistry, we call this the electron moves from a HOMO orbital to a LUMO orbital. And HOMO represents the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. So when we have that electronic transition, and how does that take place? The substance has to be given the right amount of energy at the right frequency at the right wavelength, and it absorbs that. Then we will see that transition based on the color input. So in terms of absorbance, what we're going to use today is the Beer-Lambert law. And Beer-Lambert law is this, where we have A, capital A is absorbance. This epsilon value is molar extinction coefficient, or some people call that molar absorptivity. C is for concentration. L is the path length. Most machines will usually operate at a 1 centimeter path length. Concentration, you can either be given that or you can find that. The molar extinction coefficient is really kind of the strength of the substance, if you will, especially if it's colored. Dye stuffs, this is a very important tool for dye stuffs or dye chemists, if you will, when they're looking at the strength of the dye. If it has a higher molar extinction coefficient, then typically you don't need much to impart a color with that particular substance. And polarity certainly can affect that. I should also say that solvent and temperature can also affect whatever the absorbance happens to be. We're going to measure the transmittance from our machine, and it's easier. The transmittance is a linear scale, the absorbance is a logarithmic scale, so it's easier to measure the linear values rather than the logarithmic values. So we're going to measure the percent transmittance, and then you will convert that to absorbance. And then once you have the absorbance, we're going to do two different things. We're going to find what the Lambda Max value is. We're going to scan the radiation, if you will, from about 480 nanometers to 600 nanometers. And what you're going to do is you're going to record the transmittance and then convert that to absorbance. Once you have absorbance, you're going to plot absorbance versus the wavelength, and the wavelength is in nanometers. Now this is just a schematic here. You can plot your own points, obviously. But these points that you see correspond to, if your absorbance was here and the wavelength was here, this is where you would plot your points, so on and so forth. You connect the dots here. And this is a typical curve of a UV vis spectrum. It's usually fairly broad, and at the top of that, we call that the Lambda Max, which means that's the wavelength of maximum absorption. If it's maximum absorption, then it would be lowest transmittance. So you'll plot that, and the reason we're doing this experiment is that we're trying to figure out what the Lambda Max value is for the potassium permanganate solution. The second part of the experiment is where we're going to plot the absorbance against different concentrations. And again, you will record the value as percent transmittance, then you will convert that to absorbance, and then you will plot that against the concentration. I'm just going to call these solutions 1, 2, and 3, so on and so forth. In the lab experiment, you will calculate what those concentrations are ahead of time, and then you're going to plot what the absorbance is compared to the concentration. Now here, you want to draw the best straight line. Don't just connect the dots, just draw the best straight line. Then what we'll do is we'll take a look at two unknown solutions. We'll measure the transmittance, you will convert that to absorbance, and then let's say solution 1 had an absorbance here, then you would come over and where it crossed the line, you go straight down and that would tell you what your concentration is. So we're going to do two unknown solutions. We have to prepare the plot first. So we'll look at 6 different concentrations. We'll record the transmittance, convert that to absorbance, and then plot the graph.